A very good evening to everyone present here. My name is Saurabh, and I recently graduated my bachelor's degree last November, and I'm actually working into this particular field, which is testing general relativity using black hole images and with the Event Horizon Telescope. So I'm working on this project, which is basically testing out different modified gravities and mainly general relativity using theory agnostic approach. And in the process of doing that, we actually created a library, a Python library, which is called Gallifray, a small reference to Doctor Who, if anyone is aware of that. So given a small reference to that particular scientific show, sci-fi show. So Gallifray is basically a geometric modeling and parameter estimation framework, which we have developed using black hole images, which we'll receive using a very long baseline interferometry or VLBI, and do the parameter estimation using Bayesian techniques, which we have been doing all these days in the workshop itself. So basically, as we know that last year we had not last year, in 2019 we have some amazing phenomenal results by Event Horizon Telescope, which provided us with this image of M87. So we are going to look into similar aspects of that as to how to do the simple parameter estimation in the framework of general relativity and relativistic uh, uh, realm in which we are working with black hole images. So the outline of this talk is quite simple. So first 5 minutes, I'll be talking, or let's say 3 minutes, I'll be talking about basic, the motivation as to why exactly are we doing this, the whole theoretical background, and creating all those amazing black hole images. And the next part, I'm going to explain the basic library that we have created, which is Gallifray, totally based on Python, and how we can actually use it and how we are using it to work out different theories right now. And it's still in development stage. So just to give a brief outline, in 1915, we had general relativity by Albert Einstein. 1916, we had the very first solution of a black hole, which is Schwarzschild black hole. In 63, we had this Kerr black hole, which is a rotating version of the Schwarzschild black hole, which has some angular momentum. So what we had is we had a generalized solution in 65, where there is a charge and an angular momentum of a black hole. And this particular black hole is shown using this simple result, which is called a space-time interval, which is given by this particular Kerr metric, as we say, where the temporal components are given something like this, and similarly with other components like these. So here we have the space-time Kerr metric, and there's this Hair theorem, which we say is through the properties by which a black hole can be characterized as just its mass, angular momentum, and charge. So these are three properties that we have normally to characterize any particular property of a black hole. So we're gonna actually, so the basic thing is to actually test Hair theorem as to if we have any other properties which can determine any other aspect of this particular black hole. So to test our theory, what we have is we need to have a generalized solution of this particular black hole that we already have. Now, to have such a solution, we need to have a theory agnostic approach, which means that the theory should remain itself as in general relativity. That means that we are not doing some modifications of Lagrangian in the theory. So we just need to have a simplified version of GR. But in that GR, the space-time is actually parameterized, which means that we are having some higher order and lower order terms in order to have some extra terms which would deviate from the normal solution. So here we can see that we have this particular space-time, which is said as KRZ solution, in which we have these terms such as A, W, and D, and B, and A. So the A, B, and W, and K, these are some of the terms which are interdependent on mass and angular momentum of that particular black hole. And then there are some different, extra deformation parameters, as we say, such as like A01, A02, A03, and so on, so on. And similarly, we have terms in W1 and W2 and so on. So these extra deformation parameters, when set to 0, we recover the original solution as the Kerr metric. So that's why we need to have a generalized solution when we are trying to test our theory with the observational data set. And if those extra deformation parameters, somehow, turn out to be 0, then we can say that general relativity is still holding that. So the main motivation behind all these things is to basically find constraints on those deformation parameters and see if we have some deviation from recent results or not. And to check these things, we use the basic equation that we normally use in all the numerical routines that we have is the geodesic equation, which is given by this not so simple yet a bit complicated equation, which is a four-dimensional equation in which we have, left-hand side, we have the four acceleration sort of a thing. And right-hand side is the Christoffel symbol, which is dependent on these metric terms, these components of dt phi, dr, d theta, and d phi square. So these are the basic terms that we have, which are dependent, and we solve these equations backwards in time, which we have a numerical routine that I'll be explaining later. And this is the main equation that we use to basically solve the path of light and explain the basic phenomena, which is the shadow phenomena, which I'll explain in the next slide. So the main motivation behind doing all this thing is basically to generate black hole shadow images. So if you see an image which is right here, this is the M87 image of a supermassive black hole, or let's say supermassive compact object at the center of the M87 galaxy. Here we see that there we have a small dark region. So this dark region is actually regarded as the shadow region, which means that the path of light is actually just is just there. It's not able to escape out to the observer at Earth or at infinity, and hence we are getting a dark area. So what we are doing is basically we generate these theoretical images as to compare it with our theories in general relativity and see if we have any deviation. And in order to do so, we have different model of accretion regions of this of the surrounding accreting matter. So for this, we have an example model, which is a geometrically thick disk, where we have the intensity, which is given by this particular expression, in which G is the redshift factor, J nu E is the emissivity at some particular frequency, and DL prop is the proportional length. So we use some sort of accretion matter around this particular black hole, which will lit up the surrounding area and give us an effect of something like this image. And we generate those images, and then we try to use our existing theories to test out our own version of hypotheses. So here we have this geometrically thick version in which the accretion matter has a structure of like this, where there is some thickness at the starting, which is quite low, which is thin region, and then it expands linearly. So we have this kind of example as a model for the first task. And what exactly we do is we actually try to trace back the path of the photon from the starting region, which we have the image plane of the observer far away from the particular source, which is black hole, and the far away observer is at Earth. So we consider a sort of a screen, and in simple terms and in computational terms, when we say screen, we have a particular grid sort of a thing in which we fire photons from that particular grid, and that particular photons travel back in time, because basically we have photons coming from source to us, but here we are actually firing it away, and which is much more computationally inexpensive compared to forward ray tracing, which is coming from the source. So because then we'll have to fire a lot of data points and hence a lot of photons. So here we use numerical algorithm, which is the backward ray tracing, to trace photon backwards in time from the observer where we have on Earth, and see where those photons trace back to the emission point in that particular accretion region. And we then try to image this thing. I won't be taking much time into explaining this, but shadow emergence for phenomena, but I'll just be dwelling into the aspects as to we have the shadow image and then how we proceed further into explaining these things. So here are some sample images that we have generated using the simple thick accretion disk phenomena. So here what we have is a rotating black hole in its extremal, where the spin is in the first row is 0, which means the black hole is not rotating at all. And in the second row, we have a spin, which is 0.99, which is the extremum case, in which it is a very fast rotating black hole. And the region is quite thick, and that's why we have images something like these, in where we have the inclination around 8 degrees. We are watching it around 8 degrees from the equatorial plane, and then when we are watching it on the equatorial plane, then the images are something like this, which is around at 90 degrees. So here we have a small, we'll say as a photon ring. I don't know if you can see here. Let me just zoom it maybe. So here we have a photon ring, which is the main essence of this whole thing, which explains that there is multiple images of that particular photon, which is winding up infinite times and then coming back to the observer, which gives us another interesting phenomena of gravitational lensing.
So this is super cool, but I think you have just 1 minute left.
Okay, so sorry about that. Oh, yeah. Okay, so next, coming to the library, what we have is the Gallifray library. So what we do is we actually model these black hole images in two particular forms. First, we have the geometric form, and then we have general relativistic form. The general relativistic form, I explained it in the previous slides. The geometric form is simple, simple forms which were told in previous talks as well, where you generate simple images such as a disk or crescent-like image. So those are geometric models, and we extract the basic parameters of that image, such as the disk width, disk radius, the total flux intensity, and all those other parameters. And we use Bayesian formalism to actually extract this particular phenomenon. So I guess maybe I can just skip this thing and just came to the main essence. So this is an example of a geometric model where we have two disks subtracted or different radii of different diameter from each other, and then it is lit up. And so here's a simple example of this Crescent model, which was proposed in 2013. So we have these different as models already implemented into our library, where we have Gaussians and some advanced level models such as excess ring and excess Gauss, which can actually mimic the properties of accretion, yet not in a very ideal way, but still they can somehow have some similar effects. And this is a simple version as to how one can simply create a simple model, is simply setting up the parameters of this library and initiating with this image object we have in the models module, and then simply calling it with the sky map so that they can able to generate a two-dimensional array and present a particular 2D map of the intensity. Although this is a bit of computational expensive, we haven't yet optimized it according to our conditions, but we are still working on this thing. And we can simply also blur it using some scattering kernels, such as of the Sagittarius A star or interstellar medium. So right now we have here mimicking an effect of Sagittarius A star kernel. So we can also find the visibility amplitudes of this particular image, which is simply Fourier transforming that previous slide, the previous image, and receiving how we can see it with a radio telescope under ideal conditions. So we have some simple commands to do that, and we have tutorials which are already uploaded on GitHub so that one can simply create those images. So for model fitting this particular library, this is the likelihood that we normally use, which is a form of a Rice distribution. And it is a generalized version of Gaussian distribution, where once we have signal to noise ratio very high, it becomes back to the Gaussian. So the quantity that we normally fit is visibility amplitude. We can fit all these quantities as well, which is closure and closure phases, which are all radioastronomical quantities that we can use. And we did our best fits with these geometric models to this MET7 image, and we have found some good results which are matching with the original papers of PhD L5 and L6, where we have April 11 data of MET7, where we have amplitude, visibility amplitude, and over different baselines, the length between different telescopes on x-axis. And we have some internal library which can do this MCMC distribution plotting, which is corner plots. We have named it a TARDIS module. So it gives us some sort of flavor, our own flavor to this particular existing module. Although it takes a lot of time, we are still working on the efficiency of this thing. But right now we have this working prototype for this thing. And then I think this won't be necessary. This is just an example of reconstructing this particular image using another Python library that was created by EHT members, which is EHT imaging. And we use that library to basically reconstruct that images using simulations of radio telescopes all around the world, and use that to see how we can see that image if we have those telescopes at some particular location around the world. Okay. So the code is available at this website. You can go and pull some requests or pull some issue, and if you have any requests or any issues, you can feel free to contact us. We have these additions that will be adding up in coming time, which is space VLBI, and adding more ray tracing routines, which is adding up more models and doing more relativistic stuff. So I guess that was it. Thank you.